You're on.
Hi. Hello, everyone. I'm really excited to be here today. I flew in yesterday, so I'm speaking through a lot of jet lag right now. So number one, this talk is completely different than what was advertised on the website. And number two, I hope that you still like it and you don't ask John for your money back for this conference. So, well, so today I wanted to talk about something that I've been thinking a lot about lately, and that's caching and how we're using our in-memory data stores right now, today, in our web applications. Sometimes I think caching is something we all take for granted, but it's actually extremely important. This is what gives us our low latency. So first, a little bit about me. Like John said, I used to work at Google. I was a software engineer there. I worked on a lot of different systems, which he alluded to. Then I left Google to go work at MIT to study distributed systems. I work in a lab called the Computer Science and AI Laboratory at MIT. And then a couple summers ago, I actually did an internship at this really small startup called News.me. And then right before I'm about to start, they tell me they're buying dig.com, and we're going to relaunch it in 6 weeks. And so I don't know if you guys heard about this, but a couple summers ago, we relaunched Dig. And that was a really interesting experience, actually. And what I really focus on is this question of what makes it hard for web applications to scale. So what is standing in the way of you and just infinitely scaling your web application? What are the problems? And so to talk about this, well, I don't know why the screen turned blue, but that's okay. Anyway, to talk about this, I want to focus on Dig, okay, and some of the things that I kind of learned while I was working there. So if you go to dig.com right now and you scroll down to the middle of the page, there's this section which shows popular articles, popular and trending articles. Now, almost nothing on this page is actually computed at runtime. Everything on this page is pre-computed or cached. And that's just because it's not feasible for us to render all of this information when a user actually visits this web page. Rendering this information, computing the top trending articles, involves like looking at all of these shares on Twitter and Facebook, which are just happening constantly. And it's really unreasonable to think about running over all of this data over and over and over again. And so what do? We pre-compute. We run a process every 15, 20 minutes or so that looks at all of the shares on Twitter and Facebook and runs some algorithms and tries to figure out like what everyone's really excited about, what everyone's sharing. We pre-compute all the numbers on this page too, like the graphs you see right there. And we use a lot of different storage solutions to make this work. So we use MongoDB as our durable store. We use Redis for pretty much everything. It's a huge processing pipeline. We use its pub/sub capabilities. We also use it as like an extra large cache. And then we put a lot of the pre-computed data in memcached, so we can serve it really quickly at runtime. And so, this is like kind of a very like cowboy thing to do. You're gonna like roll your own set of systems. You're caching all of this dynamic data, and I'm going to use these two terms interchangeably during this talk, caching dynamic data or pre-computation, as I like to call it. And so today I want to talk about that, what's good about it, what's bad about it, and what we're going to do in the future. So first let's talk about the good, okay? Why do we pre-compute to begin with? Well, let's look at where we are today in 2013. We are operating over extremely large data sets, so even our real-time applications are looking at tons of data. Users want incredibly low latency. Our apps actually issue really complex queries. Like, we're not just doing key value store lookups. We're doing really complex queries like friend-to-friend network queries over a lot of data. And we want to process a lot of real-time updates. It's not like that data's static, so we can just figure it out once and then never have to change it again. Users are constantly creating data. And so pre-computing and caching helps with all of this. First, if we compute the answers ahead of time, then they're going to be in memory and ready to serve when the user comes to our website. It also gets rid of the database as a bottleneck in our serving path because usually we serve this pre-computed data out of a cache. And it also gives us an opportunity. So oftentimes it's much more efficient to compute something and then apply writes to it incrementally instead of expiring it and recreating it from scratch. And so I'm going to go into detail about a few more examples of websites that actually use pre-computation a lot. So first of all, Facebook, they developed their own specialized storage system for the social graph. Then Twitter actually pre-computes everyone's timeline ahead of time and keeps it up to date. And then finally Reddit, which does a ton of pre-computation in order to render subreddit pages and user profiles and things like that. Okay, so first Facebook. So Facebook has this system called Tau, and they built this system Tau specifically to serve their social graph. So here I have a picture, and this is what would be stored in Tau to represent this check-in. So Alice is checking in at All Your Base, and she's checking in her friend Bob, okay? And so we have like 4 different objects here. We've got Alice, we've got Bob, we've got All Your Base, the place that's being checked in, and then the fact that it's a check-in. And then what these gray bars are they're the relationships between all of the different items in this graph. Alice is friends with Bob, Bob was tagged in the check-in, Alice created the check-in mentions All Your Base. And so even for this very simple status update, we've already generated like 8 different edges to put into a graph. And Facebook needs to look at all of these edges, figure out what the permissions and privacy settings are, and then at runtime decide what to actually show the user. Like maybe Carol is friends with Alice, but Bob has really strict privacy settings, so she can't actually see this. And so here's an example of what Twitter does, okay? So Twitter, like I said, pre-computes everyone's timeline ahead of time. And a timeline in Twitter is a list of tweets sorted by time of all the users that you're following, basically, just in case there's someone here who doesn't know what Twitter is. And so when a new tweet comes in, what happens is they actually fan it out to a bunch of Redis servers. So every time someone that I follow tweets, they copy it into the timelines of every single user who's following them. And there are some users in Twitter, like Justin Bieber or Lady Gaga, who have tens of millions of followers. And so what they're doing is every time Justin Bieber tweets, they're copying that, well, for active users, into every single active user's timeline. And this service is called Tflock, by the way. Okay, so Reddit, is known as the front page of the internet. And Reddit seems fairly simple. Like it's like you collect a whole bunch of links, you vote on them, you comment on them, they get resorted. And I want to talk about that sorting for a second. So almost every page on Reddit can be sorted in a ton of different ways. So you can sort by hotness score, you can sort by recency, you can sort by like what's rising and interesting or what's controversial. And what's interesting is that Reddit doesn't actually resort anything at runtime. What they're doing is, ahead of time, they're pre-computing every single page sorted in all these different orders. And they maintain that in Cassandra. And every time someone votes, they have to go and look at all these various lists and figure out how to twiddle the lists and resort things on the page. Reddit's code, it's really cool, is all open source. You can go to GitHub and just take a look at this. And so to go into a little bit more detail about that, what that means is that whenever a user votes on a link, okay, what happens in their system is that vote gets put on a queue, and then when the Reddit processes get around to processing the vote, they take a look at it and they figure out, okay, here are all our cached pages. If you voted on a link, like a picture, and that picture's in r/pics, then they go and look at all the different sort orders for r/pics and figure out if they need to change them because this link just got a vote. Okay, so what I've described here right now is pretty good, okay? A lot of really big websites use pre-computation and caching to get good latency. And they're doing a great job of it. It's awesome that we can do this. There's also a lot of choices. All these systems like Facebook, Twitter, Reddit, they're all using different data stores, and they've all sort of developed different kinds of solutions. And that leads me to the bad. Unfortunately, it's incredibly hard to do this correctly. So I just described 4 different teams, and we have 4 completely different solutions to this problem. It results in a ton of code. How many people are there at Facebook working on Tau? Probably a lot. So here's the code that does what I described a few minutes ago. So this is the code in Reddit that processes a vote that's been put on the queue. Each link is represented by 3 or 4 different kinds of pages, and we have to go and update all of these things, and we actually end up having to do 14 or 15 updates every time a single user votes. So what's really bad here is that all these sites are doing the same thing sort of in general, and I hate it when people are rewriting the same code over and over and over again in slightly different ways. We end up, what we're doing here is we're actually rewriting a lot of database functionality inside of our applications. And this is okay sometimes. I mean, that totally makes sense occasionally. But more code means more code to test, more code to maintain, more code to debug, and probably more code with bugs. So there's a greater likelihood of bugs as we have more code, and it's also harder to change around your storage strategy when you've hard-coded it into your application. But I think there's an answer out there, actually. I think that if we take a look at some research, and I'm an academic, if we look back at years and years of database research, we might actually find some techniques that could help us out with this. So let's take a look at Twitter again. This is one of the simplest examples. And you might have noticed here that this is actually a join. So this is a join in SQL syntax, plain and simple. We are joining the followers with their posts and sorting by time, and that produces timelines. And what we can do, what actually database semantics has given us the ability to do, is we can express that and say that what we're making by writing out a SQL statement that actually says, this is what we want to create, and it's called a view. So what we have here is this is just formally writing what we talked about before, and Twitter doesn't do this. It doesn't create views. This is all in code. But what we're doing is we're essentially saying, hey, timelines are just a join on these 2 tables, and this is the generic definition of a timeline. And so really quickly, just in case, I'm going to go into what a view is to begin with. So a materialized view is basically pre-computed data and caching inside of the database. It's the database word for what we've been talking about this entire time. So except for the fact that a view is created from a SQL statement instead of code. And so a view will end up looking just like any other table in your database. And you can query it just like any other table in your database. And one really cool thing is that database technology has progressed to the point where for almost any SQL statement, we actually know how to automatically keep that view up to date. So if you do an insert on base tables, then we know the database can know automatically how to take that insert and apply it to whatever your view is. You don't have to write the code to do that, which is really cool. And so let's look at Twitter again. And so what that means is that if a user posts, if we do a new post, the database can automatically figure out how to apply that to the view. And so one big question that we should think about is, well, can these applications that I described, Facebook, Reddit, Twitter, they're pretty complicated. Can they even be expressed in SQL? Who would want to do that? That sounds kind of crazy, right? And some definitely can't. Some are very complicated, and what they're doing can't be expressed semantically in SQL. But at a high level, actually, every single application I just described could be described with a SQL statement. I'm not saying you'd want to, but I'm saying that you probably could. These data structures are not actually that complicated, like sorted lists or simple joins. And so you might be wondering, well, why would I ever want to do that? And the answer is because you can reduce the amount of code that you're writing. So let's think about what we have to do if we are going to do what Twitter does right now and create this service called tflock, and we want to maintain timelines. We want to pre-compute everyone's timeline and store it like they do. Well, first we have to write the code to create the timeline from scratch, because we probably can't store every user's timeline, and in fact they don't. They just store the active users. But if an inactive user logs in, we've got to figure out how to create their timeline, right? So we've got to write that code that goes and looks up a user's set of friends, and then looks up all of the posts that they've written, and does sorting and whatever, and figures out what the timeline should be. All right, next we have to write code that maintains what's actually in our cache. So if we have this timeline service and we're pre-computing people's timelines, then we have to write the code that handles new tweets or new follows or whatever and updates that. And so we have to write the update code as well, and we have to write the update code for every single possible action a user could take. So if there's a new tweet, if a user deletes a tweet, we have to go and like fan out to all the timelines and delete the tweet. If someone follows someone new, then we've got to go grab their tweets and incorporate them into the timeline. Or if someone unfollows someone, then we have to go and like remove all their tweets from our pre-computed timeline. And so even in this very simple example, this is like one of the most simple examples, we're already having to write a lot of code in order to create and update what we're caching. But in SQL, this is like one statement. And encapsulated in that one statement, and I really think this is like kind of beautiful actually, encapsulated in that one statement is instructions on how to do all of this. So just by creating this one statement, you know, we've told our system, this is what I want to get out of it, and this is how you create it, and this is how you update it. And there's actually a ton of research on this. So database researchers have been working on this for years. They've done a lot of work on how to do this efficiently. There's just a lot of work out there. But I don't know if you've really noticed, but no one actually uses materialized views in practice. Or maybe someone out here does. And does anyone out here use materialized views in their database? Okay, I see 2. Okay, 3. Okay, that's great. So this like thing that I think is really awesome, no one's actually using. And here's why. I'm not saying you should be. I'm not saying you should run out and use materialized views in your database right now, because there's actually a lot of problems with them and the way that they're implemented in databases today. So why aren't we doing this? Why isn't everyone using like, oh, this awesome thing where you just write one statement and you know, we don't have to worry about caching anymore, and we don't have to worry about expiring things and whatever? Well, one reason is because when we're using materialized views in the database, we're limiting ourselves to the database. All of this processing is happening in one place. Another reason is because, and this is a problem that I find with databases in general, is that it's really hard to exploit application semantics in your database. It's really hard to express like staleness policies and inconsistency policies and things like that. Another reason is because we're moving into this world where more and more code is happening on mobile phones and browsers, and caching is happening on mobile phones and browsers. And honestly, what's happening in our database doesn't have anything to do with that. They're completely different systems. And so we need tools and we need understanding that helps us cache in places other than the database and memcached. And then the final reason is that there is a huge lag between what's happening in research and what's actually available to be used today in open source options. So let's talk about the first one, centralized processing. So this is the way that databases work right now. You create these giant queries, these really big, you know, select join statements and aggregates. Maybe if you have a really fancy database, you create a view. And you feed these things to your database, and then the database churns away, optimizing and like looking at tables and statistics, and figures out how to execute these queries for you. And this is an ideal for many reasons. So first of all, this is a lot of work for your database. Query optimization, query processing, it's a ton of work. And honestly, for how many of you is the database the bottleneck in your system? Okay, a lot more than 3. So your database is already the bottleneck, and I mean, I don't know about you, but I don't want to give it even more work to do just to materialize some data. This eats CPU cycles. Another problem is it's really hard in the database to take advantage of another server's memory. So you're kind of, it's just, you know, it's a fact of life today. Like, sharding your database is hard. There's going to be a lot of talks on that today, and I'm sure they have awesome techniques, but if you can get away with it, you really don't want to do it. But if you could throw in extra memory, that would be awesome, right? But it's really hard to do that today. And second, aside from writing the view and writing the query and maybe a couple other things you can twiddle, you don't actually have a lot of control over how this gets executed. So, you know, I don't really write production web apps today, and even I have had like struggled with the MySQL query optimizer, like banging at it saying, why aren't you using this index that I made? Why are you doing the join this way? And so it's really hard to give this kind of information to the database when we know how we want to execute the query. So the second reason is databases aren't really so great at this is, well, like I said, it's hard to exploit application semantics. And here's a quote from a Facebook engineering note. As efficient as MySQL is at managing data on disk, the assumptions built into the InnoDB buffer pool algorithms just don't match the request pattern of serving the social graph. And so I want to talk about that for a second. The way that databases use memory is generally through the buffer pool. So they're caching pages of your table. They're caching entire ranges of your table. And oftentimes, that's just not the right level to think about caching. When we think about the way a lot of applications cache today, you cache at the very highest level, not at the very lowest level. You want to cache computed data, not base data. And then the third reason, as I mentioned before, the database doesn't help you with caches on your browser or what you're caching on your mobile phone. So even if you had created this awesome materialized view for your database that described what a Twitter timeline looked like and all this stuff, you're still going to have to write all of that update code and creation code on your mobile client. And then the fourth issue, and this is the one that frustrates me the most because I don't completely understand it, is that open source options just tend to lag behind the research by a lot. So about a month ago, Postgres 9.3 came out, which is really cool. It's got a bunch of features. One of those features is materialized views. This came out, I believe, on September 9th. This is one of the first papers published about efficiently updating materialized views. It was published in 1986, 27 years ago, and we finally get the feature in Postgres. So just to summarize really quickly, these are all the reasons why, even though I think the idea of declaratively stating what you want to compute is great, that databases just are not working for us right now. Okay, so that kind of summarizes the bad. We have code complexity issues if we are pre-computing and caching, and we have to manage that ourselves. And databases, unfortunately, aren't practical right now to do this automatically. So that brings me to the future. So what does the future look like? Well, one thing that's probably true is that things are going to get even more mobile and more browser-oriented. So we're going to keep pushing more and more application code to these endpoints. We're moving to a world of fat clients, if we're not there already. And if the bulk of application code is in the client, then each user who's on their device, on their browser, or on their mobile phone, is going to be seeing a view, essentially, of the application's data. Because we can't fit the entirety of an application's data on a user's browser or on a user's phone. And so what happens is we have to be very careful about what data we actually put over there. And if all of our application code is over there, then we can't just act like we're operating over all the data anymore. We have to think about exactly what we're going to transfer and at what point we're going to transfer it. So applications are going to have to work across all of these systems: the application server, the application cache, the database, the client. You're going to have code spread out over all these systems to think about how to keep the client up to date. And in fact, we might actually get to the point, hopefully, where people don't, or web application developers at least, don't need to run their own backends, don't need to manage their backends themselves, which would be really awesome. We could use this thing called backend as a service. But what that means is that whoever is providing this backend as a service needs to provide the right abstractions so that application developers can efficiently use that backend. So as we continue writing our own stuff, like here's what our systems end up looking like. We have a cache on the mobile phone or on the browser. We've got our application servers running memcached. We have some kind of a database, maybe it's sharded, maybe with materialized views, but definitely with a buffer cache. And at every level, essentially, we're caching data in some form. And so that means that at every level, we're deciding in our code and in our minds, okay, where do I want to keep this data? Where do I want to cache it? Do I want to keep this in the client and then send little diffs, or do I want to keep this in memcached? Like, how do I make sure it's updated? How do I expire it? And what's even worse is that each layer uses its own abstraction for this cache. So in the browser or the phone, you've got SQLite or HTML5 stuff. On the cache, it's like a key value store. On the database, it's SQL. It's like different across every single thing. And we have to write specialized code to handle every single layer as well. And so this raises the question, okay, we have to make all these decisions. Where specifically do we want to cache data? Is it more efficient to cache it in memcached or to cache it in the client? And we also have to figure out how we want to keep that code up to date. And there are some JavaScript frameworks, actually, that have been developed recently to help with that. And I think these frameworks are really awesome. So I'm only going to talk about 3 of them, though I know there are many more. One is Firebase, which is essentially a backend as a service. So they're providing you with a backend, and their promise to you is that they will help keep data synced between your users' browsers really quickly. This company, Asana, in the US, who works on productivity software, they have this system called Luna. And one of my friends works at Asana, and I got to talk to him about Luna and the ideas behind it. And it's really cool. They were like very much ahead of their time thinking about this. At Luna, or at Asana, they run the same code on the client as on the server. So the server is actually running JavaScript and emulating a browser. And what they're doing is the server's like emulating a browser, and they sort of like say, okay, well, let me apply this data change to the state. And they figure out how that changes the data and the state in the browser. And then they just send that diff over to the client. So they have this like fairly complex system of generating diffs to send to the client. And then Meteor. Meteor is this, this new framework being developed actually by some undergrads from MIT, which is really cool. And the guy who started Meteor came from Asana. And it's doing something very similar, but they have like a slightly different spin on it. Instead of like the server like generating diffs, they've just said, let's write our code as though there's a database on the client. So let's just have it all packaged over there. And the client, and we're going to work to keep data in sync between the client and the server. So these are all awesome, and it kind of sounds like they're solving some of our problems. But the issue is that none of these abstractions is optimized for complex, high-throughput data. Facebook is not going to move their social graph to any of these things because they're just not optimized enough. They're just not going to work. And so let's take a look at what we've learned so far. So we've learned that pre-computation is actually vital. We could not run dig without it. It helps us reduce latency when we're figuring out what to show the user. We've learned that incrementally updating can be really efficient and really effective. And there's actually a ton of research in databases about how to do incremental updates efficiently and when it's efficient to do it. We've learned that declarative programming, so SQL, creating views, actually has some huge positives, namely that you can write a statement once, and that tells the system how to execute the statement, how to update the result of the statement, and it also gives the system the definition it needs to figure out how to optimize that execution. And we learned that we probably want to do all of this stuff not in the context of a single complicated server, but across several different servers and across several different layers. And so I think, and this is what I'm working on right now at MIT, I think we should think about caching and pre-computation as data flow. And so what we really need is we need an abstraction. We need the right abstraction that works not just in a database, but across multiple systems, and like the database, the cache, and the client. And in this framework, we should be able to write one statement which expresses our computed data. And we should be able to tell our systems application level knowledge. Like, we should be able to give the system the information it needs to know about what we are okay with being stale, or what kind of inconsistencies we're willing to tolerate to make the right trade-offs for performance. But in order to do that, we need not only the right abstraction, but also systems that know how to optimize pre-computation. We need systems that can look at our descriptions and can look at our input, our application level knowledge, and can figure out when it's right to pre-compute data, when we should compute it from scratch, and how to keep that data up to date. Like, what's the best strategy for keeping that data up to date based on our read and write load. So unfortunately, I don't know exactly what this looks like yet. And that's part of the reason I wanted to share it with you, actually, is because you guys are out there building and running real web applications. And I want to talk to you about whether you think this could work, whether this is a good idea, whether it fits the problems that you're actually seeing. Like, I think this is what the future should look like. I don't think people should be writing customized code for every little thing. I think that there are enough commonalities between what we're all doing that we can draw them out. And so imagine this world where you can write one statement which, for all levels of your system, so the same statement that describes what data looks like at every level of your system. And as application writes happen, the system can take care of automatically propagating them to a cache, to a database, to other clients. And that our system has enough information to choose at what level is the right place to materialize what kind of data. All right, so this is my idea for the future. Instead of the ugly, out of the good, the bad, and the ugly, an end-to-end abstraction and system-managed caching. And that's pretty much it. So thank you so much for listening to the talk and for listening to my ideas, which have no concrete implementation yet. But I would like to talk to all of you about it. So here's my contact information, and I'll be around all day. So thanks.